Hello, everybody. My name is Hemant Sharma, and along with me today is Gavin Dikiewicz. And and some of you might know that we we organize the Hull Deformity course every year. Unfortunately, it was cancelled last year because of COVID. But hopefully, we'll be doing it this year, and hopefully face to face as vaccine rollout is coming out quite well. Uh, so we're going to start I'm going to introduce the faculty and tell you about today's webinar in a minute. So I want to tell you just a couple of minutes about the deformity course for the time being. The deformity course is every year in June. It's a very good time in UK if you're coming from abroad, probably the most beautiful time, lovely long days and blue skies and all green. And it is usually in two parts. We're in the 3 days for the full deformity planning and the workshops and along with the cadaveric lab. And the last day, we do a joint subspecialty day. And that is usually done with somebody. And this year we have a Kurgan, the Elizarov Center, Kurgan, where Elizarov initially practiced and worked. So we're doing a joint day with them. On the day we'll be talking about current concept and updates in the limb reconstruction. So all the new and new things and some wanky things and whatever you think is in the line, we can they all would be discussed. We also would be doing probably on 22nd. This is the first time we are trying this year a pre-course day where or some of the less experienced delegates in a certain field, like for example, in hexapod deformity, hexapod planning, and or any 6-axis frame planning, something like that. We'll be working and giving them some lectures and some workshops and working around to help them so they're all ready for the course. So this year the course would be roughly about 5 days, starting from 22nd Tuesday to about 26th Saturday. Today we have our webinar is on oblique plane deformity.
Great.
All right, guys, let me introduce Professor Zhang.
Let me step back. There we go.
So, Simon, thank you so much. So Professor Zhang works in Beijing, is probably after Kurgan is probably the largest limb reconstruction center in the world. He has treated hundreds and hundreds of patients of any condition you can name of. He has done extensive work on diabetic feet and deformity corrections. And he's, again, very well known around the world. He is the secretary of and would be organizing the next Assami in 2023 in Beijing, which you all would be invited. And I can tell you from my previous experience from China, it would be an extremely wonderful experience. So I'll pass it on to Professor Zhang.
Thank you. Thank you. I'm very glad to come here to join the Hugh course. I know it's the famous course in the world. Thank you, Professor Sharma. Thank you, Professor Kuwait. Thank you all. My great honor.
Do you want to start sharing your screen so we can start?
It's okay. It's okay.
Thank you.
Sorry, I'm later for I missed the number of the course, so a little late. And I will share my slide. Is okay now?
Yeah, that's fine.
Thank you. Thank you. This is Dr. Zhang from China, Beijing. My institute, Qin Shihe Orthopedics Institute in Beijing. Now I transferred the college, Peking Uni Medical College, PUMC, and do some research I think the topic today, oblique plane deformity, is very important for the deformity planning. So this is my professor, Professor Chen. We pictured in Kurgan. So different place, different time. In Beijing, it's 11 p.m. But in London, it's 3 p.m. It's different time. But deformity is same. The principle of deformity correction also same. So in our center, we have a lot of deformities like this, skeleton deformity, and some soft tissue unbalanced deformities, so like this. And how to correctly evaluate the shape of bars. So you can see front view, back view, and lateral view. So similar thing, how to evaluate the limb deformity, especially the skeletal deformity, similar like the car. We have the axis like the X, Y, Z, so very important to evaluate the deformity. So before the evaluation, before the planning, we must have the standard X-ray. Standard X-ray, we can make the mate with the radiologist. We can make a team with them and make the standard X-ray, and then we can clean the deformities. We have the deformity planning of the basic knowledge. We have the point, line, and the plane, the coronal plane and the sagittal plane deformities. We have like this. Coronal, we can analyze like this. So the sagittal deformities, we have like this. Usually, we know that. How is oblique plane deformity? So in my slide, in 10 minutes, we can share some definition of the oblique plane deformities. And then I want to talk the measurement of the oblique plane deformities. And then the method for management oblique plane deformities. So the three parts. I think the first two is mainly. Firstly, what's the oblique plane deformities? What's oblique? So the definition is very important before we talking about something. That means the coronal and sagittal plane are the standard reference plane. Yes, you know that. And the X-ray, AP view and lateral view correspond with these planes. It's no problem, it's common thing. So if there is an angulation on both coronal and sagittal planes, it means deformity on the oblique plane. This is the definition. So like this X-ray, we found it in the book of Pelly. So I think it's standard book for us, also the textbook. From this view, we can the AP view is Weiger's deformity like this, 22 degree. Lateral view, the anterior deformity, pre-Weiger term, 21 degree. So both plane we can find the deformity. So is the oblique plane deformity. And the deformity other than those on the frontal or sagittal plane are the oblique plane deformities. These deformities were previously known as biplanar deformities. However, this description was wrong because they were n-planar, uniplanar angulation deformities in the oblique plane. So like this X-ray we found. So there is a plane in which the limb appears. So you can see appears straight view. Yes, this view. The limb is straight. Why? is perpendicular to that is a plane is angulation like this. So this is the right view for the angulation. So the IPQ direction of angulation is very important for understanding the oblique plane deformities. So you know that coronal plane is the medial and lateral view. That means the vagus and the varus. A little hot, sorry. And the sagittal plane, we can see that anterior and posterior, like you know, pre-vacuum and the recurvatum. So the oblique plane deformities for each axis view, there's an apical direction of angulation. Like the chart shows that we can see two possible apical directions for each plane of angulation. So you can understand this. Oblique deformities can be in any plane. So you can see that chart, any plane. As a combination, oblique plane deformities can be classified in 4 types according to the direction. So you can see here anterior, medial, and anterior lateral, posterior, and medial, posterior lateral. This different combination and present different deformities like this. So how to identify is the method for measurement. How can we clearly know the details for the oblique plane deformities? This is important for the surgery. Before surgery, you must know the plane, the level, and the direction and the degree of the deformity. How can we know that? So the second part is most important. So like you know, the C-arm is very important thing, very important device or tools. It can convert a new plane. Why I can say that? If the deformity in the oblique plane, if we give the C-arm like this direction, it's like straight. So we use the C-arm, got a straight view. So perpendicular is the degree of the is oblique view. So that's a very important tools, the way to identify. Usually we have the AP view and the lateral view in the X-ray. If the coronal and the sagittal deformities, we can evaluate directly. So how to evaluate the oblique deformity in the AP view and the lateral view is a very important thing. We must know that the relationship in the space. So the degree of the true angulation in oblique plane can be calculated in trigonometric formulas, a little difficult for the common doctors. So based on the reference, we know Professor Ba in 1989, he published his paper in GBDS, like chart and the table. It's useful, but a little difficult. And then 1998 senior, the method from Ilijalov, he published in his book, Transverse Osteogenesis, that book. So we can see Professor Ilijalov give us some device like this, small device to evaluate the oblique or translation some deformities. And we also should combine some tables, some numbers in that, a little complex. So, and then Professor Ilijalov also knows that it's a little difficult. He found another method for evaluation the oblique deformities. It's based triangle method. So we can call it like this. So this view we can see the line, and the base, the triangle, and then this view I think is easy to understand. So you can see the red line and the blue line. The blue line, the length and the degree is the amount of the oblique plane deformities. So this is Ilij-Jarov. This method requires the beams, the X-ray must perpendicular to the bone. It's very serious requirement like that. And not so easy from the common radiologist. And so it's not used very common. So Dr. Pelly found an easy way to evaluate the oblique deformities. He named this graphic method also the 1992 years. So I think you know that similar way. I think is similar way, but a little simple. So you can this way also have some error, 4 degrees error. Even that is easy way. So a lot of doctors want to use the easy way to evaluate the oblique plane deformities, include me. I think the steps are very important. So step 1, draw photos like this. We know which side, left or right, which side. When we draw some grooves, think about ourselves from up to look down like a bird. You know which side, left or right. Step 2, you can see here, labor. Labor is very important. Left or right, we can decide medial or lateral side, similar to ourselves. And then mark the magnitude of angulation. From the AP view and the lateral view, we can mark the degree on the axis like this. In AP view and the lateral view, so lateral view, material, and anterior, posterior, so marked the number here. This is step 3. And draw a line from the origin to the over point. This is very important for the direction. And step 5, measure the length of the line, and measure the angle between the line and the axis. 3, indicate the direction of the apex of the oblique plane deformities. Like this, the right photos, you can understand. And step 6, the final one, in the box, so we can know the degree, the plane direction, and the apical directions of the deformity like this. These steps of the evaluation. So I want to give a case so we can understand easily. So you can see here, in the front view, we can see is a little virus deformities like this. From the X-ray AP view, 20 degree. The side view and the lateral view, we can see 35 degree. It's oblique plane deformities. Absolutely, yes. So, how can we accurately to evaluate the degree? We must think about the method, the graphic, or some Ilij-Jarov, or Pelly's, or some method. Yes, somebody absolutely want to use the C-arm. We use the C-arm to evaluate it directly in the radiology department is easy, but the patient delivers this AP view and the lateral view come to the clinical room. How to do? We give the graft, yeah, and then we mark AP, ML, we mark. So we want to recover the steps, and then when combine the numbers here from the AP view and the lateral view, we mark here is the anterior and the posterior, and the lateral and the medial. So we think ourselves is left side, myself, left side. So here is M, here is L, here is the 20 degree, here is the 35 degree. So we marked here, and then we draw this line. This line is very important for the deformities. 45 millimeter equal to 45 degree, the deformities. Watch where is the plane? So this is the plane, this is the plane, deformity plane. So because the plane here, we know the angulation correction, the ACA axis is here. So based on this method, we can give the patient the hinge correction method. So this X3, this is the clinical view and surgery after surgery. So remove the fixator, we got the good result. So in the summary, we can see the oblique plane is uniplanar angular deformities, not bio. To understand the level, plane, direction, and the degree of the deformity is very important before we perform the surgery. So this is the second part. Is the third part, I think is method for deformity correction. I think also important. And based the two before, maybe Professor give me just the definition, just what's the oblique plane deformities. So I wanted to give the third part to other professor. And so you must know that the beta tor. How to correct the beta tor with the finger? Yes. No. So can we use the Idijalov? Yes, we can so. So that's the V. We can talk about the oblique plane deformities like the oblique beta tor with the Idijalov method or other method. So in the end, we would like to say thanks to a lot of friends in the world, Professor Hamashama, Professor Gama Hasni, Professor Nayagam, Professor Pali, and Song, and Katani. And they give us so many acknowledgement and some opportunity to share, to discuss, to say hi to the world, the friend of world. Because last year, the very serious fight, the COVID-19 come to around us. We can't see, we can't face-to-face to communication. It's very bad, but I think we can meet in internet, very nice. Thanks, Professor Hamashama. And finally, we wanted to give my best wishes to all. In Chinese, 平安 is safe and healthy. Thank you. And I think in my part, I showed it was the oblique plane deformities. For the correction, can I ask my partner what's the topic of you and some content of you, and then we continue. It's okay?
Agreed. Yep.
Gavin?
I think it was very good. Thank you very much. That was excellent. Introduction to our deformity. The oblique plane, as you say, is an important deformity to understand because it is quite common. You know, most fractures and fracture non-unions, malunions, and deformity work, most things occur in an oblique plane, not in the traditional planes that we talk about. So thanks very much for that. And now I think we can go on to Simon to continue with elucidating this method of evaluating and looking at and correcting the oblique plane deformity. Thanks, Simon.
Okay, thank you. Thank you again. Can everybody hear me okay? Yeah. Right. So I hope my slides are shown on your screen, folks. Is that okay?
Yeah, we can see you.
See, and can you hear?
We can hear you as well.
Lovely, thank you. Right, just give me a sec to find the play button.
So just remember, everybody, please use the question and answer button. If you have any questions, queries, or things you want to discuss specifically or ask the faculty, please make use of the time.
Lovely, thank you. So as we said earlier, good afternoon, good morning, and good evening to everybody. It's good of you to join Professor Zhang. Well done, you had us worried slightly. So I'm going to move on slightly from what I thought was a very good description, a very good demonstration of why oblique plane matters. I'm going to talk to you a little while about one of the ways in which an oblique plane deformity can be corrected, and that is using a traditional old-fashioned circular frame and a Lizaroff frame with hinges. Obviously, this is one of many ways this can be done. People use hexapod-like devices, people use internal metalwork. I think if you can understand how one would correct an oblique plane deformity with an Lizaroff frame, that helps you to understand the importance of everything that Professor Zhang has just said to us. So I hope to repeat a little bit of what he said and then perhaps move us on and maybe show you why understanding this surgical technique helps you to understand the basic principles. So this is a sort of a summation of what Professor Zhang has just said. There is not an AP and a lateral angulation. There is one angulation that lies in an oblique plane, and therefore, because of an angulation, it has a site and it has a magnitude and it has a direction. And there is only one deformity. If there is a single angular deformity, it can be defined. You can define its site and its magnitude and its direction. And you can do it by trigonometry, by drawing lines and measuring them and using graphs. Those of us that are old enough can remember how to do it by algebra. Or you can, as Professor Zhang said, do it by direct measurement, either using an X-ray department or the image intensity in theatre. And it's fortuitous that I've got a picture which just complements his. So, can everybody see the right-hand side of the screen? There is a deformity
Simon,
behind that. I'm sorry. Yeah?
Simon, your color palette bit is coming on the screen as well.
Oh, hang on.
It is just in front of lateral view.
Yeah, so, let me see if I can. Is that hidden you all?
No, it's still there.
Can you delete the palette at all or move it off the screen? Just can you grab it?
I can, yeah. Just give me a second and move it out of the way.
You probably have to go undo your screening. Go back to. So stop presentation for a minute.
Yeah, no, there we go. Right, so if I can get rid of the palette.
Can you just minimize the palette, Simon? Or...
I think that should do it, should it?
No, it's still there.
That one.
Yeah, that's it. Great. Thank you. Perfect.
We're in business there. Is that?
Yeah, perfect.
Good. So moving back a little bit, I think this is my example of what Professor Zhang was speaking about. So if we look at those X-rays, this is a proper AP and a proper lateral X-ray of the tibia taken with the patella forwards, all those things that we require of our radiographers, and you can see there is a deformity visible in the AP plane, there is a portion of deformity visible in the lateral X-ray, And as we've said, therefore, there must be an oblique plane deformity, and therefore there must be a neutral view. And all we've done in this case is, if you use the patient's left foot as a protractor, what we've done here is we've rotated the foot internally, and that gets us the maximum deformity, a deformity larger on that X-ray than either of the deformities we saw in the previous film. But we also get a true neutral plane deformity where we're looking, as Professor Zhang said, right into the base of that deformity. So armed with the maximum deformity, we can define its site, we can directly measure its magnitude, and if we know the relative angle of the foot and therefore the relative angle of the X-rays, we can even work out the third thing, the thing that I think a number of people struggle with, which is the direction of the deformity. So this is just another example. You obviously have to work this out, you have to understand it, but here is a way in which you can use an X-ray machine, whether it be fluoroscopy or a proper X-ray, to demonstrate the site and the direction and the magnitude of any deformity that you see. And this is rather, as we've done before in the past, if you do this with a goniometer, you get a plane AP, and you'll get a lateral X-ray, and if you rotate the goniometer a little bit, there'll be a point at which you get a slight deformity visible in the AP plane, and you get a slight deformity visible in the lateral plane, but they are simply portions of. So you need to be able to understand how to accurately define this, whether you do it by trigonometry or whether you do it by algebra. In these days of 3D printing, people are now actually starting to print bespoke bones, but I think that's rather cheating. So this is the bone we're going to use in the workshop, which is going to be the last 10 minutes or so of my presentation this afternoon. But if you look at this, you have an AP view, and you can see there is a notable deformity, and there is a lateral view with a similar deformity. So we know on the basis of this, there is an apex medial deformity, there is an apex anterior deformity. Therefore, we're going to resolve this out to find an apex anteromedial deformity. Its origin will be at this point here where the axis lines cross. But as we said, there will also be a point where if we rotate the bone appropriately, it will appear straight, and a view taken at 90 degrees to that will show us the true magnitude of deformity, which is larger than what we saw on the previous views. So this is just the same example. This is an example of doing exactly the same thing as we're showing you on the X-rays before. There is a plane in any oblique plane deformity when you have defined that plane, and once you're in that plane, the bone will look straight, and at 90 degrees perpendicular to that plane, there will be the true magnitude of deformity, which is always larger than what you see on each of the separate X-rays. So if we just go back to our traditional AP and lateral views to be going on with, I hope that most people have got sufficient familiarity with the Ilizarov frames and everything that goes with that to know that if you were to put a pair of rings exactly perpendicular to each segment of the tibia in that view, or you can do exactly the same in the lateral view as well. So two rings exactly orthogonal to the tibia, and you were then to join them together with hinges right on the apex, right on the convex surface of the deformity. In each view, as you straighten those up, the tibia would come out to straight. And if you do exactly the same thing in the oblique plane, and this is what we're going to start working out in a minute, as long as this proximal couple and the distal couple are perfectly orthogonal to their segment, when you take this straight X-ray, when you rotate the limb or you rotate the fluoroscope, the frame will look perfectly straight. If you then rotate to 90 degrees, so you're looking across the maximum deformity, again, this couple is perpendicular to the proximal segment, and this couple is perpendicular to the distal segment. Therefore, this deformity, the true deformity which centers here, the true overall deformity is modeled precisely by that frame, by the hinges therein. And we know, I hope, that if you build this correctly and the top couple is parallel and the bottom couple are parallel to their respective segments in all views, as you line things up and as you straighten up the frame, when the frame becomes straight, the bone will become straight in all aspects. So it's not just that it will straighten in the AP plane and the lateral plane, but it will also straighten up in all aspects. And again, if we look into the true plane and the perpendicular plane, obviously in the true plane, when we're looking into the deformity of the tibia or of the frame, which are exactly the same things, that will not change. It will still remain straight. But when this is truly perpendicular, so if you start out with the frame exactly perpendicular top and bottom, and you line this all up, as it straightens, the tibia will come straight, the axis lines will coincide, they will overlap, and the frame will have moved by much more overall in this single view than it did in either of the separate views. And I think if you can grasp that, as long as the couples are perpendicular to their segments, and as long as the hinges are sitting right on the apex of the deformity, right on the convex surface, what I'm about to show you, and I'm just going to show you a little video, hopefully will make sense. Please do not go away with the idea that just because you can do it by building it on the table, you don't have to do all the planning and all the thinking. Remember, the essence of limb deformity is you measure everything to make sure you're not leaving yourself any surprises. We all know people who think they can do it and who've got caught out. Do not think that because you're going to do this with a hexapod or with an internal device, you don't have to understand, you don't have to do all the planning that we've talked about all through all the courses that we've done. This is simply one method of using a particular device to correct a deformity once you have confirmed that you know how to accurately measure and define the device. So if I were to stop there, and I think I'll agree with Professor Zhang, so that's the end of the introduction, if you will. If you do have questions and you want to pop them into the Q&A boxes, please do. But what I'm going to do with permission is I'm just going to show you a brief video which is edited down from a workshop that we did on the whole course 2-3 years ago. It's been edited down by me, so do please forgive me if it looks like live news. There is no sound on the video, so I can talk over the top and perhaps show you the important things. So unless anything burning flags up in terms of the questions at the minute, I'm going to move on and show you the video if that's okay.
Yeah, that's fine. There are no questions coming up just a moment, so carry on.
Right. Not any questions, Gavin. Do you have them?
Yeah, there are no questions at the moment, so carry on.
Okay, so I say this is very edited down from a much longer version of an oblique plane deformity workshop using hinges that we did in Hull 3 or 4 years ago. So hopefully there is no sound, and I'm just going to do that thing of talking over myself and walking you through what I hope are the key steps as I do this operation in real life. Do please bear in mind this is done with workshop kit, so that's why we've got a steel 5/8 ring and carbon fiber complete rings. Why these rods look too long for the frame, that's just simply because we're doing this with workshop kit, not proper surgical kit. But again, this is all about demonstrating important principles as we go. So in terms of simple things, when I do this, I pre-build these couples often. So you need a ring couple for the proximal segment, a ring couple for the distal segment. In this, we've used identical sizes all the way through. Obviously, you can vary the length of the rods and the height, basically the length of each couple, so that you're going from your proximal fixation to your fixation near the deformity, and then near the deformity, and then your distal fixation. And I've drawn this with identically sized rings all the way through, which is not what people always do. And what this picture is trying to show you is if you look at where the rods are, which are joining the rings together in each couple, they are positioned identically in each couple, so that when the frame is straight, these rods will look as if they run perfectly straight all the way from top to bottom. I don't think you necessarily have to do that, but I think it makes for efficiency because you're only wasting a limited number of holes in each frame as you go through. But that is just to demonstrate that the rods in each couple are identically situated in relationship to connecting bolts that are holding the two halves of the ring together. And that's just going to disappear in a second. And the next thing you need to think about is how you're going to connect your rods together, how you're going to connect your couples together. So this is just a demonstration of the hinges I tend to use. I know you can buy pre-made hinges and special hinges, but I still build all of mine out of threaded rod, a high-profile female, a nut to lock the female onto the rod, and then another nut lower down the rod, which is what's going to be used to adjust that. And obviously, you need at least 4 of those because you get 2 pairs of hinges. You will also need a 3rd pair of hinges, whether you use a, oops, it's all going so well for a minute, wasn't it? It's all going so well for a minute. Bear with me, please. We were about there, weren't we? So as I say, you need to build 2 pairs of hinges at the very least. A number of people will actually build 6 pairs. When we get a little later on, I will show you what I tend to use as a hinge. This is how I tend to set my patients up as I'm doing this. You can see it is the bone more or less as we looked at before. There is an apex anteromedial deformity in this. Position the patients on the table so the proximal portion of the tibia is horizontal. It simply makes it easier to remember things. Sorry about this. I'm having trouble with the buttons. So I position the patients with the tibia horizontal, the proximal portion of the tibia horizontal, just as you would do for fracture surgery and things of that nature. I think it's easy to remember, it's easy to think. And then I always pass my proximal reference wire first. I accept there are people that use half pins. I accept that people may do this in a slightly different order. But I find if I put in that proximal wire first, it gets me moving, it gets me going, and I know where I'm up to. So that mounts there, and then what we're going to do in a second is simply disconnect that and mount the proximal wire couple to it. And I think this is one of the reasons why a wire is perhaps easier to do this with than a half pin. So we're going to rest the 5/8 ring of the proximal couple on that wire. You'll notice there's a rod straight down the front of the frame. So the frame ring, the true rings in the frame are joined together with the bolts more or less directly front and back. And I do that because it allows me to use this rod to make sure that the frame is directly perpendicular to the tibia in the AP view. Because if you've got the rod and you've got the tibial crest, you can be fairly clear that things are well aligned in what's the AP view. Now, obviously, we did this as a workshop, so we don't have an image intensifier, but what we do have, and I'm going to show you this in a second when this comes around, is obviously if you've got a rod directly down the front portion of the frame, and you know where the proximal tibia is, you know where the tibial crest is, there we are. So that section is just to demonstrate that rod line perpendicular to, parallel to the tibial crest. And this view in a second is to show you that in the lateral view, that rod would be perpendicular to the tibial crest as well. So at this stage, with 2 wires and this, we have now got this couple directly parallel to the tibia. And what we're going to do now is obviously we would ordinarily put many more wires or connection elements into this. What we're doing now at the minute is exactly what Professor Zhang talked about, is we're now rotating the leg and we're using the lateral view, which is simply the camera in the audience, to look at the tibia at the point at which it looks perfectly straight. And obviously, if it looks perfectly straight when it's looked at in a lateral view, when looked at from directly in front, that is the maximum deformity. That is the true magnitude of the deformity that we're working with. And therefore, it is here at this point that we need to position our hinges to get a pure opening wedge correction. And these are the hinges that we've built. And what we're doing here is we're just mounting one of those on the anterior part of the frame, so directly overlies that deformity. And we're going to do exactly the same thing in a second, directly over the apex of the deformity in the posterior portion of the ring. So at that point there, as we said, there is half a hinge here which lies directly in line with the apex of deformity, and there is one just off the top of the screen at the moment, which is the anterior half a hinge. So we now have a couple which we know is parallel to the tibia, and we now have hinges which are positioned directly front and back on the apex of that deformity, right on the convex side of that deformity, because as you can see there, I think we've rotated the tibia so that it is horizontal when it's looked at in a lateral view, and therefore the AP view, the vertical view, shows you an exact size and magnitude for the deformity that we're dealing with. We're then going to move on very slightly in a second. A reference wire at the bottom, and obviously the bottom half of the frame is more or less exactly the same as the top half of the frame. Use a reference wire, mount the hinges on the distal couple in exactly the same holes on the middle ring as they were on the distal ring of the top couple, because that is where the correction correction has to take place. That is what we've defined by our preoperative planning, but it's also what we've just proved during our surgical procedure by rotating the limb with respect to the image intensifier or vice versa. So again, we're simply proving that the proximal couple is parallel to the tibia. We're now building a hinge, and if you look at the hinge that's on the distal of those two rings, or at least if I just move my hand out of the way slightly. So can I convince you, can you see that there is the join in that ring, there is the join in that ring. This, the half hinge on the proximal ring, is directly over the fracture site, over the deformity site, because that's what we've measured. It's what we expected it to be from our planning. And all we've done now is we've put hinges in exactly the corresponding hole on the distal ring, on the distal couple, and we're now simply going to join those together. So we should then have a couple parallel, exactly parallel to the proximal segment, a couple exactly parallel to the distal segment, with hinges which are equally spaced around all the rings which we've used at the level of the fixation. And as I say, this is the fiddly bit. But as I say, I think that the great joy of doing this way is it proves to you that your planning and your trigonometry or your algebra or however you've done your planning, if you have planned everything correctly so far and up to date, once you've got these hinges joined together, you should have a frame which exactly corresponds to the deformity you have in the bone. Because your proximal segment is under the proximal couple, your distal segment will be under your distal couple. These two hinges here will be exactly, if we were to x-ray this vertically, exactly projected one over the other in that vertical x-ray, that x-ray that shows you the maximum deformity. And there will be a point somewhere about here where these rings are maximally convergent, where the deformity is so truly reflected by what's going on that you could even use count the holes in the ring to tell you exactly where the base of the deformity is. So I'm perhaps just going to scuttle this forwards a little bit, if that's all right. I don't think you necessarily need to watch people putting wires into a frame, but we will get to the point very soon where I think it's about there. So if we look there now, so we've now reverted to an AP X-ray, more or less, because you can see this rod is exactly down the crest of the tibia as it goes. Okay, we can now see, you imagine if we were to just shift the camera slightly over there, if we look down exactly over this bolt, it would line up exactly with the apex of the deformity, and it would line up exactly with this hinge, which I've cleverly hidden from you with my thumb. And there is also a point slightly round the corner, which we're going to come to in a second, where in the lateral view, or the perpendicular view, the tibia is exactly straight in the correct view as we go. So just bear with me a little bit as we go. What we're going to do is, with any second now, the camera's just going to walk to the other. So there we go. So that is there. If you look at that, that is the view looking directly into the deformity. So just see that there just before it moves off. On that view, which is with the tibia significantly rotated, the tibia looks straight in that direction. The hinges that we've placed will be directly here, front and back. And all we're doing at the minute is just putting an extra complex hinge here just to do our deformity correction. But there is a point where, with exactly that same view, with exactly the same rotation between the tibia and the image intensifier, or in this case, camera, where the tibia looks straight because we're looking right into the base of the deformity. Then we're just going to cut the bone as we go, and just because this is plastic bone, we're just going to snap it and line it up straight. And as we say, as we snap it at that stage, there, the tibia remains completely straight when you're looking at it in that orthogonal plane, that plane which looks straight right into the deformity. But also when we lift this all out and show a true AP X-ray, and it's difficult not to show off at this stage, I'm sorry, it turns and the tibia rolls up perfectly straight. So all other things being equal, I think that's covered most ground. I think, to be fair, Professor Zhang and I have got through an awful lot of stuff between us in the last 45, maybe 50 minutes. So if I've gone over a few and I've cost you some of your morning or your afternoon or your evening, I'm sorry. I'm about to stop there. If there are some questions, let's see where we go. I'm going to turn my screen share off, so hopefully we can just see our faces. And there is a Q&A thing there.
Yeah, so Simon, there is a question, which I think is quite a good question actually. It relates to deformity correction, so perhaps we can ask our two speakers. The question really is in tips of us for osteotomy when you're doing oblique plane deformity, in order not to crush the bone, and also what would be the order of correction if you've got angulation, a length correction, and rotation. You know, how do you approach that? What type of osteotomy and what's the order of correction?
Okay, Dr. Kinnick, thank you for your question. That's a very good question. So I will tell you my thoughts as we go, and I'll perhaps then pass over to Professor Zhang. My thoughts are, if you're doing any form of axial rotation, so what we will call version or rotation around the vertical axis, which I think is what your question is. So if I'm at any point doing significant axial rotation, I tend to do a horizontal osteotomy, so I tend to use a Jiggly saw for those. If the rotational element is not significant and it's a pure oblique plane deformity as we've spoken to it, I still tend to do mine simply with an osteotome, with a small sharp osteotome and a lot of hammering. And I find that as long as my osteotomes are relatively sharp, and they are most of the time, that is what works for me. So if you've got a significant rotational element that is around the vertical axis, a flat osteotomy, and I would use a Jiggly saw. For all other forms of correction, I would use just simply a small sharp osteotome. And going back to the very last element of your question, I try to do rotation first and get it out of the way. But I accept that it's habit and practice. It's just I find it easier to see everything else once I've got the rotation correct. But I suspect if you asked all three of my colleagues, they would tell you a slightly different version. So I hope that's answered your question, Professor Kinnick.
Professor Zhang, do you want to comment on that? Do you have an order of preference? You need to unmute yourself.
I think Professor Simmons' the talk is very good. He explained for the question is very good also. For me, regarding the deformity combination, some rotation and angulation, we have the hinge deformity correction, this method. Yes, no problem, this method. And we want another method for deformity correction is, can I call it acute deformity correction. Firstly, we correct the part of the deformity, such as some rotation, we correct it partially. And then the residual deformity, we give the deformity to the hinge. And then another way, we correct all the deformities together. So in the surgery, we can give the hinge gradually deformity correction. And also we can give the way for deformity correction in acutely, in single way. In the surgery, we correct all the deformities, include the angulation and the rotation, like this way. I have a case I will show later. Thank you.
So I think a couple of important points there. You can correct some of the deformities acutely, and the remaining you can do gradually. I think if you're using a traditional Israel type technique and you're having hinges, you can place your hinges further away from the convex surface and to get a more a greater opening of the deformity to allow the bone ends to move apart so they don't impinge. If you're using obviously a hexapod when you're doing a 6-axis correction, then you may want to have your lengthening first to distract your bone fragments if you know they're going to impinge, and this can be programmed in with the variety of hexapods that we have available to us. Rotation is good to correct first, because unless the bone is exactly the center of your rings, you will create a secondary translation deformity, in which case you will still end up with further translation to correct later on. So if you do your rotation first, then you know what the translation is going to be at the end. You then can angulate, and then finally you can finally translate if you want to have an order of doing them. Remember also that if you're doing a combination of deformities, angulation, rotation, etc., take note of the soft tissues, what's happening to the soft tissues, what's happening to the neurovascular bundle, etc., because that may also determine what you do. By creating length first, you stretch the soft tissues, and that may make your rotation easier and your angulation easier in terms of unloading the system and detensioning the soft tissues. So I think that's a very important question. Thanks very much for that. And I think there's a lot of information in that.
Yes.
Great. So, Heyman, are we going to do some cases? Can we show some cases or something? Got some time for one case?
We're just about around the time, so I don't know.
All right. Are we over time already?
Yeah. So
Okay.
all I want to just emphasize is that, Gavin, I'm going to just share the slide again. So two things. One is for the deformity course, which we have talked about, but also our next webinar is on the 10th of April, again on Saturday. It's on update on deformity of the management and osteogenesis imperfecta. And Reggie Hamdi from Montreal would be there, along with James Fernandez from Sheffield. They both are very well-known pediatric surgeons. So please do join us. And also today's webinar would be available on our YouTube channel. All you need to do is, if you go on YouTube, just type Hull Deformity Course, and there are previous webinars. This webinar will come in about a week or so, and along with some other educational material available for you if you want to see that. Thank you.
Excellent. Thanks very much to our two speakers this afternoon. I think it's been great. It's been great having you and listening to you all again, and I hope all goes well for the remaining weekend.